Modelica is a mathematical modeling tool that involves representing physical systems around us in the form of symbolic representations. It is a programming language that uses the interactions between different components in a system to model how it behaves when faced with certain inputs. Modelica is used to model cyber physical systems that are used in diverse applications. These systems feature the integration of hardware and software components interacting with each other through control algorithms. Input data from sensors feed through to the control loop that parses this data, applies it to governing equations, determines output characteristics, and then feeds these through to other sensors, algorithms, or hardware components. This integration of software in hardware components is like the Internet of Things that is present to a large extent in our everyday lives. However, IoT features low-level computation and is usually just a basic implementation of software control to hardware. For instance, setting your favorite song to play as soon as you open the main door to your house is based on two sensors that check whether the door is open and if motion has been detected. On the other hand, cyber-physical systems often involve multiple sensors and actuators acting together to feed and gather data. The control loops in CP systems are also computationally intensive and may feature large datasets, complex algorithms, and real-time control. Modelica is a prominent programming language that excels at modeling CP systems. Being symbolic, Modelica differs from conventional programming languages used in engineering applications, notably MATLAB, in that it features equations to represent complex systems. MATLAB is a numerical solver. If you wish to determine the value of an integration, this solver would split the integrand into smaller sections and then apply Simpson's rule or the trapezoidal rule to obtain the desired value. In this implementation, the programmer would need to explicitly define the function and the method using which the calculation should be done. Numerical solvers suffer from inaccuracies since it ultimately represents an approximation. On the other hand, Modelica is analytical and only requires the governing equation, i.e., the integral expression to be defined. It then solves this problem using DAE methods with better performance and accuracy. Now, how can we use Modelica to represent a complex cyber-physical system? We start by defining the inputs and outputs for each component of the system. These represent the features of a component. For instance, the length of the spring is a feature that represents it. We then identify the governing equations or define the behavior of the system. A linear spring exerts a force proportional to the length of extension or compression, and this defines the behavior of the component. Lastly, we define the interaction between the components. This tells the solver how to link the spring to a mass and to the reference ground. Lastly, by solving the governing equations of each component and then analyzing the system as a whole from the relations between each model, the total outputs of the system can be determined. Any data that is measurable, continuous, and linked to a component can be provided by Modelica. If you recall, I mentioned that Modelica is a programming language. And just like any other language that needs a compiler to run, Modelica needs a solver engine to take the lines of code and make sense of them. This is where Modelica engines come into play. There are certain industry leaders in this domain, and Maple stands out for its world-class multi-body solver MapleSim. It also has an easy-to-use interface that makes it an excellent choice for GUI-based system modeling. Now that you have had a quick introduction to Modelica and MapleSim, let's jump straight into an example of modeling a system in MapleSim. This is the MapleSim graphical user interface used to run Modelica components. On top, over here, we have the simulation toolbar that allows the user to control the simulation time, check the solver for diagnostics, build and run a system, and display the simulation results. To the right, we have the component properties panel that can be used to control how the parameters of the model change between simulations. By heading into the solver controls, the user can change the simulation methods, including the type of simulation, the time step, solver method, and other features. At the bottom, we have a diagnostics and console output that shows the user how the simulation progresses and if there are any errors or warnings. To the left, the user can use components from the Modelica standard library, and when we import custom libraries, they appear in this panel. For our example, let us build a simple spring and mass system. In MapleSim, the GUI allows users to simply head to the library of their choice, find the component they wish to use, and then click, drag, and drop it onto the workspace. It's as simple as that. We begin building this model by importing a mass, spring, and ground, with the ground serving as reference for the motion of the spring. We head into the parameters panel for each of the components and set the desired values. We also need to specify what we want to measure, and we use a probe for that purpose. We can choose the different measurable quantities and then run the simulation. Running the simulation takes a few seconds. The user can explore these plots by selecting the type of cursor, the number of plots they wish to see in a row, and explore the results using Excel or a CSV format export. Now that we have our simulation results, I'm going to save the result in MapleSim for future reference. Let's say we want to build a custom component using this GUI. I want to create a new component that behaves like a damper, but the force exerted by it is proportional to the acceleration and not the velocity. The simplest method to execute this is to deploy a component from the library into the workspace, and this can be done by simply clicking, dragging, and dropping. We then right-click and select Create a Custom Component, which takes us to this file. I then edit the code accordingly by first changing the name of the file such that the component name also changes. I then replace all instances of relative velocity with relative acceleration and define it as a double derivative of the displacement with respect to time. Once done, I hit save, and if there are any errors, they will appear at this stage. Now that the file has been saved, I can find that a new custom component has been created over here. It is labeled custom1, and I drop that into our workspace and get rid of the old one. By connecting the components together, I can then rerun the simulation. And if you rerun this, you will find that the simulation results have changed, keeping in mind that the new damper or the new component takes into consideration the acceleration and not the velocity of the mass.